Reflection means the bouncing back of waves from the interface of the two media. The bouncing back of a wave from the interface of the two media is known as a reflection. For example, let us consider the surface xy, which is separates to two media. This is first medium, this is the second medium. Now, a sound wave is made to incident on the surface like this. Suppose a point O on the surface xy, and this point O is called point of incidence. The wave which is incident on the surface at the point of incidence is called incident wave. This is incident wave. After the reflection from the surface, the wave travels along this direction. This is called a reflected wave. A perpendicular line drawn at the point of incidence is called normal wave. A wave which is incident on the surface is called the incident wave. The wave which is coming from the surface is called the reflected wave. A perpendicular line drawn at the point of incidence is called normal line. Right. Here, the angle between incident wave and the normal line is called the angle of incidence. The angle between the reflected wave and the normal line is called the angle of reflection. Angle of incidence and the angle of reflection. Angle between incident wave and the normal line is called the angle of incident. The angle between the reflected wave and the normal line is called the angle of reflection. The reflection of a sound obeys laws of reflection. Obeys laws of reflection. According to laws of reflection, the angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. So this is first law. Suppose if the sound wave is incident on the surface at an angle of 30 degree, it is reflected with the same angle, that is 30 degree. If it is incident on the surface of 45 degree angle means the angle of reflection also 45 degree. So it obeys laws of reflection, right? And second one, the incident sound wave or incident wave, reflected wave and the normal line at the point of incidence all lie on the same plane. All lie on the same plane. Here plane is the surface of the board. So on the surface of the board, that is a plane, there is an incident wave, reflected wave and the normal line. Okay, all the three lines exist on the same plane. So this is second law of reflection. So according to first law of reflection, the angle of incidence is equal to angle of reflection. Second, the incident wave, reflected wave and the normal line at the point of incidence all lie on the same plane. All lie on the same plane. So this is laws of reflection. The reflection of the sound wave obeys the laws of reflection like a light. Right. Let us consider a sound wave. It is a travels in air medium in the form of a compression and a rarefaction. Right. So there is a sound wave which is travels in air medium, which is travels in the form of a compression and a rarefaction, and it is made to incident on the boundary of a rigid surface, suppose wall. Right? So here the sound wave is travels in the form of a compression and a rarefaction and is incident on the outer boundary of the wall or outer boundary of the denser medium. Outer boundary of the denser medium. Right. Here the compression of the sound wave is incident on the boundary of the denser medium. If the compression is incident on the outer boundary of the denser medium, it is reflected as compression. It is reflected as compression. Right? When the sound wave travels in air medium in the form of a compression and a rarefaction, If the compressed region is incident on the denser medium, it is reflected as a compression. It is reflected as compression. Suppose if the rarefaction is incident on the wall, it is reflected as rarefaction. It is reflected as rarefaction. Right. Suppose the sound is travels in denser medium. That is a solid denser medium. Right. Here also it is travels in the form of compression, rarefaction, compression, rarefaction, and compression. Right. Here sound wave travels in solid denser medium and it is propagated in the form of compression and rarefaction. Now the compression is instant on the interface between solid and air medium. Instant on interface. This is the interface between air medium and solid medium. Here compressed region is instant on the interface between solid medium and the air medium. Right. Here if the compression is instant on the interface between air medium and the solid medium, it is reflected as rarefaction. Suppose if the rarefaction is instant on the interface between a solid and air medium, it is reflected as a compression. It is reflected as compression. Right? If the sound wave travels in air medium and instant on a denser medium, the compression is reflected as a compression. If it is instant on the surface, that is rarefaction is instant on the surface, it is reflected as rarefaction. The same sound wave is travels in the denser medium. If the compression is instant on the interface between solid and air, it is reflected as rarefaction. If the rarefaction is instant on the surface, it is reflected as compression. So this is the reflection of a sound wave at the boundary of the denser medium and the rarer. Boundary of the denser medium and the rarer medium. Right. And next topic, echo. Echo is nothing but a repetition of a sound due to the reflection of sound waves from the various rigid surfaces. From the various rigid surfaces is known as echo. Suppose if you make a sound in front of a high mountain, you can hear the sound you produce repeatedly. Okay, you can hear the sound you produce repeatedly. Right? That repeated sound is known as echo. Even the sound produced by you is stopped, the sound is coming continuously from the mountain. So that repeated sound is known as echo. Right? And there are two conditions for hearing an echo. First one, the minimum time conditions for hearing an echo. The first condition is the minimum time gap. The minimum time gap between incident wave and the reflected wave. Incident wave and the reflected wave should be 0.1 second or 1 divided by 10 seconds. The sound is produced from the source, which is travels towards the obstacle, and after striking the obstacle, it is 1 second reflected towards the source. Right? So this is instant wave and this is reflected wave. The minimum time gap between instant wave and the reflected wave should be 0.1 second or 1 divided by 10 seconds. So this is first condition for hearing an echo. Right? And the second condition, the minimum distance between the source and the obstacle. The source and the obstacle should be 70.2 meters or 1/20th of the velocity of a sound in air medium. 1/20th of the velocity of a sound in air medium. The minimum distance between source and the obstacle should be 70.2 meter or 1/20th of the velocity of a sound in air medium. If these two conditions are fulfilled, we can hear an echo. So there are two conditions second or 1 divided by 10 second. And minimum distance between the source of sound and the obstacle or a reflector should be 70.2 meter or 1/20th of velocity of sound wave in air medium. Velocity of sound wave in air medium. Right. Okay. The applications of echo, applications of reflection of sound are also there in our book. They are theoretical region and easy region, so you prepare yourself. So next we go for measurement of velocity of a sound wave in air medium or any one of the medium by using echo method. And the distance between source of sound and the wall is supposed to be right. And there is a listener or an observer near the source of the sound. Here the distance between wall and the listener also the same distance, that is d. Now the source emits a sound wave. It travels towards the wall and strikes on it. After reflection, it travels towards the listener. Right. Here the total distance travelled by the sound wave is is 2d. Because first the sound wave travels from source to wall, okay, with a distance of d. After reflection, it travels from wall to listener, the same distance d. So total distance travelled by the sound wave is 2d, right? And let t be the total time taken by the sound wave travels from source to wall and wall to the listener is t, right? We know that velocity is equal to distance travelled divided by time. Here the total distance travelled by the sound wave is 2d and the time taken by the sound wave is t. So by using this relation, we can find out what is the velocity of a sound wave in the medium. So this is echo method. This is very simplest method is used to find the velocity of a sound wave in any medium. Velocity of sound wave in any medium, right? And next we go for an important topic, Doppler effect. Right. Once again, let us consider a source of sound, and there is an listener. And suppose the source emits a sound wave with a frequency n. Right, n be the frequency of the sound wave emitted by the source. Right. Here both the source and the listener are at rest. Now the listener measures the frequency of the sound wave emitted by the source. The frequency of the sound wave measured by the listener is the same as that of the actual frequency of the sound wave emitted by the source if both the source and the listener are at rest. Both the source and the listener are at rest. Right. But however, there is a relative motion between the source and the listener. Relative motion means either if the listener is at rest, the source is moving towards the listener or moving away from the listener, or otherwise the source is at rest and listener is moving towards the source or away from the source, or both source and listener are moving towards each other or away from each other. That is a relative motion. So there is a relative motion between source and the listener. Now the frequency of the sound wave measured by the listener is different from the actual frequency of the sound wave emitted by the source. The actual frequency of the sound wave emitted by the source. For example, a passenger is standing on the railway platform. A train is approaching him, or a train is moving towards him with the horn. Right. The frequency of the sound wave emitted from the horn appears to be increases for the passenger. When if the train is moving towards him. Suppose the same train leaves him, the frequency of the sound wave emitted from the horn appears to be decreases. That apparent change in frequency of the sound wave due to the relative motion between source and the observer is known as a Doppler effect. It is so called because that apparent change in frequency of the sound wave was first observed and explained by Christian Doppler. So that is why this phenomenon is known as Doppler effect. So Doppler effect means the phenomenon of apparent change in frequency of the sound wave due to the relative motion between source and the listener or source and the observer is known as Doppler effect. Right. Doppler effect is depends on velocity of source and velocity of listener. The Doppler effect is depends on velocity of source and velocity of listener. Right. The apparent frequency of the sound wave measured by the listener due to the relative motion between source and the listener is generally given by the expression n prime is equal to v minus vl divided by v minus vs into n. N actual frequency of the sound wave emitted by the source and n prime apparent frequency of the sound wave measured by the listener and v velocity of sound and v suffix l velocity of listener and v suffix s velocity of the source. Velocity of the source. Right, n prime apparent frequency of the sound wave measured by listener and n actual frequency or original frequency of the sound wave emitted by the source. V velocity of the sound wave emitted by the source and Vl the velocity of the listener and Vs the velocity of the source. The apparent frequency can be calculated by using the formula n prime is equal to V minus Vl divided by V minus Vs into n. Right. There are various possibilities of the relative motion between source and the listener. Various possibilities of relation between the relative motion between source and the listener. Right. The first one, a listener move towards or away from stationary source. Right. In the first case, source is stationary and listener is moved towards or away from the source. And second case, a source move towards or away from a stationary listener. And third, both source and listener are moved towards each other or away from each other. Right, both the source and listener move towards or away from each other. Away from each other. So for all these three cases, we can use a general or common formula, that is n prime is equal to V minus Vl divided by V minus Vs into En. Right. But one more thing, there is a sign convention must be followed while dealing with the Doppler effect. Okay, sign convention means, so for example, here source is at rest means Vs value is 0, that is velocity of the source is 0. Here listener is at rest, then we can substitute Vl is equal to 0 because the listener is at rest. Right. And this source emits sound wave. Suppose the sound wave is travels with a velocity of V. Right. Suppose the source also travels towards a stationary listener. So here Vs is not equal to 0. Here both the velocity of sound wave and the velocity of the source, these two are in the same direction. So Vs value is taken as a positive. Vs value is taken as positive. Right. Suppose if the source is moving away from the stationary source. Here the direction of the velocity of source is opposite to the direction of velocity of the sound wave. Here V and Vs are in opposite direction. So the Vs value should be taken as negative. Similarly, if the listener is moving towards a stationary source, suppose the source is at the rest, so Vs value is 0. Now a listener is moving with a velocity of Vl towards the stationary source, with a velocity of Vl. Right. Here the velocity of sound wave emitted by the source is acting in this direction, whereas the velocity of sound wave direction is opposite. So Vl value is negative. Vl value is negative. If the listener is moving in this direction, Vl and V are in the same direction, so Vl value is taken as a positive. Right. So this sign convention must be used while dealing with the Doppler effect. Right. Right. Now, first special case. A listener move towards a stationary source. Right. Case number 1. A listener move towards a stationary source. Right. This is source which is at rest. So its velocity Vs value is taken as 0. Vs value is 0. And it emits a sound wave of frequency n and with the velocity of V. So this is the direction of velocity of the sound wave. Okay. The velocity of the sound, the direction of velocity of the sound is always towards the listener. Right. This is listener. Right. Listener is moved towards the stationary source. Suppose with the velocity of V. Right. Here VL is opposite to the direction of V, so this value is taken as a negative. That is, velocity of the listener should be taken as negative. Now, the general formula for the apparent frequency of the sound wave measured or heard by the listener is n prime is equal to V minus VL divided by V minus Vs into n. Right. V minus VL value should be taken as a negative. So, minus VL divided by V minus Vs value is 0 into original frequency n. That is equal to V minus into minus plus VL divided by V into n. So this equation gives the apparent frequency of the sound wave heard by the listener and the listener moving towards a stationary source. Right. So this is first case. Right. And next second. Away from here, stationary source. In the first case, listener moved towards a stationary source. The apparent frequency of the sound wave measured by him is given by n prime is equal to V plus VL divided by V into n. In second case, the listener is moved away from the source. Right? This is a stationary source. So Vs value is 0. And the actual frequency or original frequency of the sound wave emitted by the source is n. And this is velocity of a sound wave. And the listener is moving with the velocity of Vl. Okay. Its direction is opposite to the direction of velocity, so away from the source. Right. Here VL and V are in the same direction, so it is taken as a positive. Right. Once again, the main formula n prime is equal to V minus minus VL divided by V minus Vs into N. N prime is equal to V minus VL is positive, so answer is VL divided by V minus Vs value 0 into N. Therefore, N prime is equal to V minus VL divided by V into N. So this equation gives the apparent frequency of sound wave noted or heard or measured by the listener moving away from the stationary source. Listener moving away from the stationary source. Right. So this is second. Third case, source yes move towards a stationary listener. Stationary listener. So in the first two cases, source is stationary and the listener is moved towards the source and away from the source. We can obtain two formulas of apparent frequency. In first case, apparent frequency formula n prime is equal to V plus VL divided by V into N. In the second case, n prime is equal to V minus VL divided by V into N. Right. In the third case, source is moving towards the stationary listener. Listener is at a rest. Right. Source is moving with a velocity of Vs. It emits a sound wave of frequency N and the velocity of sound wave is V. And here listener is at a rest. So VL value is 0. VL value is 0. In this case, velocity of source and velocity of sound are in the same direction. So it is taken as positive. And apparent frequency formula n prime is equal to V minus VL divided by V minus Vs into N. So V minus VL value is 0 divided by V minus Vs is always positive, so no change, Vs into N. Then V divided by V minus Vs into N. So this is apparent frequency formula if the source is moved towards a stationary listener. Right. Fourth one, source move away from a stationary listener. Stationary listener. Right. Source is moving with the velocity of Vs. The frequency and the velocity of sound wave emitted from the source are N and V. And the listener is at rest. So VL value is 0. VL value is 0. Right. And apparent frequency formula N prime is equal to V minus here. Velocity of a source and the velocity of a sound are in opposite direction, so it must be negative. Right, formula V minus VL divided by V minus Vs into N. V minus VL value is 0 divided by V minus Vs value is minus Vs into N. Right. Then final formula N prime is equal to V divided by V minus into minus a plus. So Vs into V. So this is apparent frequency formula if the source is moved away from the stationary listener. Both source and the listener are moved towards each other. In the first four cases, either stationary, the source is stationary or otherwise the listener is stationary. But in the fifth case, both the source and the listener are moved towards each other. Right? So this is source. Suppose it is moving with the velocity of Vs and frequency of the sound wave is N and the velocity of sound wave emitted by the source is V. And the listener, so listener also also moving with the velocity of v. Right? Here both source and listener are moving towards each other. Here Vs and V are in the same direction, so it is positive. But VL and V are in opposite direction, so VL is a negative. Right? Apparent frequency formula N prime is equal to V minus VL divided by V minus Vs into V. Right? V minus, here the velocity of listener is negative, so minus VL divided by V minus velocity of source is positive, so no change, Vs into N. Right. Then V minus into minus a plus, so plus VL divided by V minus Vs into N. So apparent frequency of sound wave measured by the listener when both the listener and the source are moving towards each other is given by or can be calculated by using the formula N prime is equal to V plus VL divided by V minus Vs into N. Right. And sixth one, source and the listener are moved away from each other. Source is moving with the velocity of Vs and frequency of the sound wave emitted by it is N, and the velocity of the sound wave is V. And the listener are also moving with the velocity of VL. Right, here VL and V are in the same direction, so it is positive. But V and Vs, these two are negative, so Vs should be taken as negative. In this case, apparent frequency N prime is equal to V minus VL divided by V minus Vs into N. Right? V minus VL is positive, so no change, so minus VL divided by V minus Vs is a negative, so minus Vs into N. Therefore, V minus VL divided by V minus into minus plus Vs. If the source and the listener are moved away from each other, then apparent frequency measured by the listener is N prime. It is given by V minus VL divided by V plus Vs into N. Right. So there are various possibilities of the relative motion between source and the listener. So if the possibility changes, then correspondingly the apparent frequency measured by the listener formula also changes. Right. And in some cases there is no Doppler effect. Right. They are, first case already we know, if both the listener and the source are at rest, the listener and the source are at rest, there is no Doppler effect. That is, the frequency of the sound wave measured by the listener is the same as that of the actual frequency of the sound wave. Actual frequency of the sound wave. Right. No Doppler effect. In some cases, in first case, right, source and the listener are at the rest. Okay, Doppler effect is nil. And second, source and the listener are moving along the same direction with the same velocity. There is no Doppler effect. And third, if a source and the listener are moving perpendicular to each other, suppose the source is moving upward and the listener is moving along a horizontal direction. Right. here angle between them is 90 degree. If a source and the listener are moving perpendicular to each other, okay, now Doppler effect is nil. Doppler effect nil. And fourth one, if the source lies at the center of the circle along which a listener moves, or otherwise listener is at the center of the circle and along which source moves. So in this case also Doppler effect is nil. If the source and the listener are at the rest, there is no Doppler effect. Source and the listener are moving along the same direction, with the same velocity. That is VL is equal to Vs. In this case also no Doppler effect. And third, source and the listener are moving perpendicular to each other, no Doppler effect. And fourth one, if the source is at rest at the center of the circle along which listener moves, or the listener is at rest at the center of the circle along which source moves, the Doppler effect is nil.